Hello students, welcome to InstaOwl Science class where we believe in democratizing education for all. In today's lesson, we will continue our discussion on the topic the human eye and the colorful world. In the previous video, we have already learned about the fascinating properties of light, and now we will focus on another important property known as dispersion. To begin with, let us understand the concept of dispersion of white light. Dispersion is the phenomenon of splitting white light into a spectrum of colors when it is passed through a glass prism. When a ray of white light enters the prism, it undergoes refraction due to the change in medium. However, instead of bending uniformly, the light separates into different colors. This spectrum consists of 7 distinct colors arranged in the following order: violet, indigo, blue, green, yellow, orange and red, commonly remembered by the acronym VIBGYOR. These are the constituent colors of white light. Each of these colors bends by a different amount upon passing through the prism. The difference in bending is due to the varying wavelengths of each color in the visible spectrum. Red light bends the least because it has the longest wavelength, while violet light bends the most because it has the shortest wavelength. Hence, when white light is passed through a glass prism, we observe a band of colors, proving that white light is a combination of multiple colors, each refracted differently. Let us now perform a simple experiment to observe the dispersion of light through a prism. To begin with the setup, take a thick cardboard sheet and make a small hole or a narrow slit at the center. This narrow opening allows a fine beam of light to pass through. Now, let sunlight enter through this slit so that a narrow and focused beam of white light is produced. This beam is essential for observing the splitting of light clearly. Next, place a glass prism in such a way that the light from the slit falls directly on one of its faces. What you will observe is a beautiful band of colors forming on the screen. This is the result of the white light getting dispersed inside the prism into its constituent colors. This band of colors is known as spectrum, also called as the white light spectrum, which visually confirms that white light is made up of multiple colors. Let us now understand the famous experiment conducted by Sir Isaac Newton on the white light spectrum. Newton was the first to demonstrate that sunlight is made up of a spectrum of colors. He achieved this by passing sunlight through a glass prism, which caused the white light to disperse into its component colors. This was a significant discovery as it provided the first scientific explanation for the formation of a spectrum. In his initial experiment, Newton attempted to split the spectrum further by passing it through a second prism. However, he observed that no new colors were produced, indicating that the spectrum was complete and not further divisible. He then proceeded with a revised version of the experiment. This time, he used a second prism placed in an inverted position relative to the first. The spectrum of colors produced by the first prism was allowed to pass through the second inverted prism. To his surprise, instead of seeing the spectrum again, Newton observed that white light emerged from the other side. This led to a significant conclusion. The experiment showed that the white light is made up of multiple colors, which can be separated by a prism and then recombined using an inverted prism. In simple terms, the first prism disperses the light into a spectrum and the second prism recombines the spectrum back into white light. Thus, Newton's experiment not only demonstrated the dispersion of light but also proved that white light is composed of 7 visible colors that can be both split and merged through the appropriate arrangement of prisms. This leads us to the phenomenon of the formation of a rainbow. A rainbow is a natural spectrum of colors that appears in the sky typically after rainfall, when sunlight interacts with water droplets suspended in the atmosphere. The cause of this phenomenon is the dispersion of sunlight by water droplets. When sunlight enters these droplets, it is refracted and separated into its component colors. These water droplets act like tiny prisms, similar to how a glass prism disperses white light in a lab experiment. The entire process involves three main steps. First, the sunlight is refracted and dispersed as it enters the water droplet. Next, the light undergoes internal reflection inside the droplet. Finally, it is refracted again as it exits the droplet, directing the dispersed colors outward toward the observer. This sequence of interactions, refraction, internal reflection, and the second refraction leads to the formation of a visible spectrum. This is why we observe a rainbow consisting of 7 colors, commonly remembered as the acronym VIBGYOR, that is, violet, indigo, blue, green, yellow, orange, and red. In conclusion, the rainbow appears due to the dispersion and internal reflection of sunlight within water droplets, producing a beautiful arc of colors that can be seen in the sky after rain. Let us now understand the concept of refraction in the atmosphere, which explains why celestial objects like stars appear slightly displaced from their actual positions. The main cause of this phenomenon is the gradual change in the refractive index of the atmosphere. The atmosphere consists of multiple layers of air that vary in temperature and density. As we move downward, the air becomes cooler and denser, while the upper layers are hotter and less dense. Because denser mediums have a higher refractive index, the refractive index increases progressively toward the Earth's surface. Light traveling through these layers does not move in a straight line, but bends gradually due to this continuous change in refractive index. This bending of light always occurs towards the normal because it is moving from a rarer to a denser medium. This is a direct application of the law of refraction. Now, let's apply the concept of atmospheric refraction to a real-life observation. The apparent position of a star in the night sky. When starlight enters the Earth's atmosphere, it passes through layers of air with varying densities. Each layer causes the light to bend slightly towards the normal as it moves into progressively denser air closer to the Earth's surface, resulting in a curved ray path. However, the observer on Earth perceives this light as if it is traveling in a straight line. As a result, the star appears at a higher position than its actual location. It is an optical illusion created by the refraction of starlight through Earth's layered atmosphere. Let us now understand another real-life example of atmospheric refraction: the twinkling of stars, a phenomenon that is both visually striking and scientifically intriguing. Since stars are extremely far away from us, they appear as point sources of light in the night sky. This means that all the light reaching our eyes from a star is concentrated along a single narrow path. Due to constantly changing atmospheric conditions such as wind, temperature fluctuations, and air movement, this path slightly shifts every moment. As a result, the apparent position of the star keeps changing, and this causes its brightness to fluctuate when observed from the ground. This variation in brightness and position creates the effect we commonly call twinkling. This explanation is further supported by the following diagram. As light from a star enters the Earth's atmosphere, it travels through rarer to denser layers, bending slightly at each interface. This bending alters the light's path and makes the star appear in a slightly shifted position. However, since our eyes assume that light travels in a straight line, we perceive the star to be at this apparent position, not at its true one. As these shifts continue due to the atmospheric turbulence, we see the star's light flicker, giving rise to the twinkling effect. Now, the question arises, why do planets not twinkle? The answer lies in their proximity to Earth. Planets are much closer to us than stars, and they appear as extended sources of light, not as single points. This means the light we receive from a planet comes from multiple closely packed points. Even if atmospheric refraction causes some rays to deviate, the overall combined effect of all the rays remains nearly constant. This cancels out any noticeable fluctuation, and hence planets generally appear steady in brightness. They do not twinkle unlike the stars. Let us now understand yet another real-life example of atmospheric refraction. The phenomena of advanced sunrise and delayed sunset. During actual sunrise, the sun is still below the horizon, but its rays bend as they pass through the Earth's atmosphere due to the gradual change in air density. This bending causes the sun to appear slightly higher than its true position, allowing us to see it a few minutes before it has actually risen. A similar effect occurs during sunset. Even after the sun has moved below the horizon, its rays continue to reach us because of atmospheric refraction. This allows the sun to remain visible for a short time after it has physically set. As a result of this bending of sunlight at both sunrise and sunset, the apparent position of the sun differs from its real position, as shown in the diagram. The observer sees the sun above the horizon when in reality it is below it. In conclusion, this optical effect extends the duration of daylight by approximately 4 minutes, with the sun appearing about 2 minutes earlier at sunrise and remaining visible for about 2 minutes after sunset. Let us now understand the concept of scattering of light, a key property of light that explains many natural and observable phenomena. Scattering occurs when light rays deviate from their original path upon striking tiny particles such as dust, gas molecules, smoke, or water vapor. These obstacles redirect the incoming light in various directions. This process is particularly important in the atmosphere, where such particles are abundant and constantly interacting with sunlight. One of the most well-known examples of scattering is the Tyndall effect. It refers to the phenomenon where a beam of light becomes visible when it passes through a colloidal solution. This happens because the colloidal particles scatter the light, making the path of the beam observable. In contrast, such scattering does not occur in a true solution, where the particles are too small to affect the light path. To observe the Tyndall effect experimentally, consider two beakers. One filled with clear water, a true solution, and the other with a colloidal mixture, such as milk mixed with water. When a flashlight is directed at both, the light beam remains invisible in the clear solution but becomes clearly visible in the colloidal mixture due to the scattering of light by suspended particles. In the atmosphere, a similar effect occurs on a larger scale. Air molecules, water droplets, dust, and smoke scatter incoming sunlight. This atmospheric scattering explains why we observe a visible light path in dusty or foggy conditions, and also accounts for the reddish hues at sunrise and sunset. Now that we've understood how light scattering and the Tyndall effect help us observe light paths in colloidal systems, let us apply the same principle to a natural question. Why is the sky blue? The explanation lies in Rayleigh scattering, where fine particles and gas molecules in the atmosphere, smaller than the wavelength of visible light, scatter shorter wavelengths like blue and violet more effectively than longer wavelengths like red. However, because our eyes are more sensitive to blue and most violet light is absorbed in the upper atmosphere, the sky appears predominantly blue. As sunlight passes through the atmosphere, this scattered blue light reaches our eyes from all directions, giving the sky its characteristic color during the day. But what happens in the absence of an atmosphere? In outer space, where there is no medium for scattering, light travels undisturbed. So, without atmospheric particles to scatter sunlight, the sky appears completely dark. A similar effect can be observed at high altitudes, such as in mountainous regions or aboard high-flying aircraft. Here, the atmospheric density is lower, meaning fewer particles are available to scatter sunlight, and hence the sky appears darker than it does at sea level. Let's explore some important facts with our InstaBites. Did you know that eyes can be donated after death to help the blind? In developing countries, 35 million people are blind, including 4.5 million with corneal blindness, and 60% of them are children under the age of 12. Anyone, regardless of age or sex, can donate, including spectacle users, cataract-operated individuals, and those with diabetes or hypertension. However, individuals with communicable diseases such as AIDS or hepatitis are not eligible. The procedure is quick and straightforward. Eyes must be removed within 4 to 6 hours after death by contacting the nearest eye bank. Eye banks collect, evaluate, and distribute the donated eyes while maintaining complete confidentiality. If unsuitable for transplant, the eyes are used for research or educational purposes. Remarkably, one pair of donated eyes can restore vision for up to 4 people. With this, we come to the end of the chapter Human Eye and the Colorful World. Let's summarize what we've learned using InstaLights. We began by understanding the concept of dispersion of light. When white light passes through a glass prism, it splits into a band of 7 colors, violet to red, forming what is known as the spectrum. Moving ahead, we saw atmospheric refraction, where light bends due to changing air densities, leading to the shifting of the apparent position of celestial objects. This concept helped us understand formation of rainbow, where tiny water droplets act as natural prisms, dispersing, reflecting, and refracting sunlight to produce a spectrum of colors in the sky. Finally, we understood scattering of light, where atmospheric particles deflect light in different directions. This explained natural phenomena like the blue color of the sky and reddish hues during sunrise and sunset. This concludes our topic, the human eye and the colorful world. Keep watching our InstaOwl videos for upcoming topics. Thank you and goodbye.